Okay, back from the break again. Continuing with power dissipation, and talking about two different types of power dissipation, which are dynamic. Which one is the switching transient, and that's during the transition from 0 to 1 or 1 to 0. The NMOS and PMOS transistors are simultaneously on for a brief time. That provides a conducting path from VDD to ground. So you get a current spike during that transition. Transient power dissipation during switching can be estimated from those current trajectories we saw previously. And basically we're going to look at a worst case estimate and assume the device is operating at maximum frequency or a minimum period of TF plus T rise, and we'll assume that the total current Imax is flowing through those devices. So we're going to go to our equations there, make a couple assumptions. We're going to sort of look at worst case, so Vn is equal to VDD by 2. Threshold voltages, let's say VDD by 5, and the strength of the pull-up and pull-down transistors are the same, in which case when we're able to calculate a value for Imax in terms of beta and VDD. So overall upper bound for the energy dissipated per cycle then becomes the power dissipation during charging and discharging CL and that of switching itself. So in this point here we're just looking at the switching part. So if the period increases, the power dissipation would still be present, but of course it would go down. If the rise and fall times increase, then the power dissipation could vary as VDD cubed, and we'd estimate that by holding the input at VDD by 2 and seeing what happens. We wouldn't be constrained any more by the T rise and T fall. That's what it amounts to. So circuits which tend to be power hungry as a result of switching transient can often be sampled or gated if it's a problem, and convince yourself of that by drawing a simple gate, and an easy gate to use for that is this, an AND gate. So the energy dissipation per cycle, if you work out all the details, is going to be on the order of 2/5 CL times VDD squared. Now we're looking at the second aspect, which is charging and discharging the capacitive load, in which case the power here is going to be equal to, let's say, IP times VDD minus Vout plus IN times Vout. So basically we're getting a discharge current, let's say when we're discharging CL. This is that current IN, and the voltage at that point is Vout. So we end up multiplying the voltage times the current to get those the values of power. This will be a slightly more complicated calculation because Vout is changing as a function of time. It's not just the power supply voltage. But we're going to simplify our arguments and to sort of look at this type of circuit here where we charge and discharge this capacitive load through these two resistors, one being the pull-up resistor and one being the pull-down resistor. And they're basically the resistive models for our MOSFETs. So during the discharge phase, we're going to go from 0 to TP by 2. And it's going to be IN times Vout, and we're going to integrate that from 0 to TP by 2, which we were saying we're operating at minimum period or maximum frequency. And the same thing for charging, slightly more complicated expression, but it's only by virtue of the fact that we're worried about the voltage across the PMOS device, which is VDD minus Vout. And this will be the current flowing flowing into the capacitor through the PMOS device. So TP is 1 over FP, where FP would be the maximum frequency operation. In this case here, we know that IN is equal to minus CL VODT, and then we have a similar expression for IP, which is this current flowing into the capacitor. So the power dissipation becomes, and really it's energy per cycle, it becomes an expression that looks like this now when we discharge from VDD to 0, or we charge from 0 to VDD, plug in those values for the currents from the previous page, and we see we end up with a fairly simple expression, which is the frequency times the capacitive load times the power supply squared. So this is a reasonable approximation for power dissipation. Well, it seems to be, because power dissipation increases as the frequency increases, as we'd expect. We're switching the device or charging and discharging the capacitive load more frequently. Power dissipation increases as the voltage increases. Well, we have to deliver more charge to the capacitor, and we have to deplete more charge off the capacitor when we're discharging it. A simpler and more physical analysis can be also easily derived by going back to our original little circuit there and just worrying about it in this scenario where we're pulling up through RPU and pulling down through RPD. So we just consider that situation. Switch goes to position 1. We're going to charge CL to VDD, so that's through the pull-up. And we just look at the total amount of charge delivered. It says IDT. Integrate that over whatever time period it takes to charge that thing up. And we know that we're delivering Q, which is CL times VDD. So the energy delivered by the source is just VDD times this thing up here. and it's just CL by VDD squared. So we know energy stored on the capacitor is 1/2 CV squared, and that would be the same then as the energy dissipated in RPU. So it's energy delivered minus the energy stored. So the total energy dissipated by charging discharging CL is the energy dissipated by RPU and the energy dissipated by RPD. So the energy dissipation per cycle becomes CL VDD squared. So we're going to worry about that at some particular frequency. We'll just end up multiplying that by the frequency, so it's F times CL VDD squared, just as we had previously from a slightly more complicated derivation. Another way to look at that, if you like, would be just in terms of a work being done. So this is a very similar type of expression. We're going to end up with saying the energy required to move the charge onto the capacitor is CV squared. Half it is stored, and so half it is dissipated. So the total power dissipated by an integrated circuit is the sum of the static and dynamic terms. The dominant part is almost always going to be the dynamic power dissipation, and this is worthwhile remembering. The power dissipation varies linearly with frequency and quadratically with the power supply voltage. So that's one of the main driving forces to reduce VDD. Reduced voltage will also facilitate actually making faster devices. That's contrary to our expressions for T fall and T rise, which were approximations. But the rationale is that we can make faster devices by making everything smaller, and they'd be able to operate at lower voltages. There are some design alternatives, perhaps a variable voltage circuitry. So for a given technology, it might be feasible to improve the speed of some critical circuitry by increasing the power supply locally, so within a small region. I can't imagine that's that easy to do. So there'll be lots of difficulties, and some of these may be related to the fact that you're injecting maybe more carriers into the substrates, and these may cause other unwanted problems such as potential latch up, maybe having more difficulty telling whether the device is on or off. Other alternatives, of course, cool the chip, and that could be liquid or air. And one of the technology drivers, as everybody probably is aware here, that they would be the gamers, and here's someone with a relatively novel do-it-yourself type of cooling system for that chip being used in some type of game, probably overclocked like crazy, and maybe the voltage is cranked up as well. Some design alternatives, some approaches for improving performance might be to combine something like CMOS and bipolar devices on a single substrate. That's been called bi-CMOS, or would be called bi-CMOS. Other things might be gallium arsenide type of implementation, which is very specialized. But there has been some interest in gallium arsenide for very high-speed digital analog. And there's some difficulties with that, or maybe some other circuit techniques you might use, such as emitter-coupled logic. You can probably also add carbon nanotube to this list of pretenders, because the way that's often phrased is these are technologies of the future, always were, always will be. Not to say that the carbon nanotube might not have a role to play, but it's been around for a while and hasn't really made much of a dent anywhere. So the champion still is vanilla CMOS. That's really good vanilla. It would be Baskin-Robbins type, and here's just the trophy for vanilla CMOS, and here's a picture I took from IBM. It's just a photomicrograph, but it's a neuron type circuit. So here they're not really interested too much in speed, because eventually they want to build something that tends to look like a brain, and if you're not really pushing speed, you can get lots of density, and perhaps you'll get complete architecture changes in the future. Anyway, this brings us to another break, and we'll be back after that.